Good afternoon, everyone. It is a great honor and pleasure to introduce Chris Wilson to you today. Chris is visiting from McMaster, is here actually until July next year on sabbatical at MPIA. Chris is a world-renowned expert on spectroscopy in the submillimeter and far infrared of the interstellar medium, mostly in external galaxies, in particular also in extreme environments like ULERGs and LERGs. She did her undergraduate studies at the University of Toronto, and then in 1990 got her PhD at Caltech, where in 1987 she discovered Comet Wilson. So we have a comet explorer in our midst now. So then, since 1992, she's been a professor at McMaster University in Hamilton, where since 2001 she's a full professor, and since 2015 a distinguished university professor. From 1999 till 2014 she was the project scientist on behalf of Canada for ALMA, and between 2014 and 2016 she was president of the Canadian Astronomical Society. And today she's going to talk about to us about dense gas and star formation in nearby starburst galaxies with ALMA. So let's give her a very warm welcome, and the floor is yours.
Thanks. Okay, thanks very much. Is the mic okay? Yep, sounds like it. All right, well, so it's really nice to be here to be able to tell you about some of the recent work that my students and I have been doing, working primarily with data from ALMA to look at the question of gas and star formation in nearby galaxies, with a particular focus on extreme galaxies like starbursts, mergers, and luminous and ultraluminous infrared galaxies. So what I'm going to do in my talk today is I'm going to start off by giving you an introduction, giving you a little bit of background about why we look at galaxies at submillimeter wavelengths, and also what we know from other people's work about the relationship between dense gas and star formation. I'm then going to give you a bit of an introduction to ALMA. I'm sure you've all heard of ALMA and you've seen ALMA data. I'm going to tell you a little bit about how ALMA works as an interferometer. And then the main science from my group, I'm going to talk about the star formation law and some unusual CO line ratios in nearby ultraluminous infrared galaxies. And those line ratios point perhaps to a change in the stellar initial mass function. Talk about dense gas, particularly in the antennae merging system, which is the closest merger galaxy to our own, and then some new work that I've been pursuing over the last 2.5 years on trying to understand emission from cyanide, CN, which is another potential dense gas tracer in nearby galaxies. So, because I often forget at the end, I like to put my acknowledgements up the front. I want to acknowledge my former and current students, many of whose work you're going to see in this talk today, my postdoc Toby Brown and our collaborators, and the various sources of funding, both to me personally here from my research group, and also the national funding that allowed Canada to be a partner in helping to build ALMA. So just as a broad picture, why would we want to look at millimeter wavelengths when we're studying galaxies or indeed studying the universe? Well, if you look at the distribution of energy as a function of wavelength from the universe as a whole, it's dominated by the cosmic microwave background. But if you're interested in resolved sources, then you have two nearly equal peaks of energy, the optical background and the far infrared background. And so the long wavelengths in the infrared to submillimeter carry about half of the energy from individual sources in the universe. And they're particularly important for studying objects that are in the process of formation. So young stars, planet formation, and galaxy formation at high redshifts. And so if we weren't going to look at the infrared, we would be missing about half of the emission that's coming out from galaxies. So where does ALMA work in this scheme of things? That's roughly the wavelength range or frequency range that ALMA works in. Wavelengths from about 3 millimeters to 300 microns, frequencies from 100 gigahertz up towards a terahertz. So we're not at the peak of the infrared background. We're out in the Rayleigh-Jean's tail, but this is as close as we can get from the ground to the bright emission in the infrared, because these wavelengths through here are completely blocked by the Earth's atmosphere. Now, if we look at galaxies in particular, we can ask where the light from galaxies is coming out as a function of wavelength, and this is a nice figure from Frederic Galiano's PhD thesis in 2004. If you look at the bottom two plots, the green plot shows you an elliptical galaxy, and the purple plot shows you a spiral galaxy, and you can see that both these galaxies have a characteristic two-peak structure. The bulk of their energy coming out are wavelengths around 1 micron, but a secondary important peak at a wavelength of 100 microns. When you go to the more actively star-forming systems, like the starburst galaxy M82, about 3 megaparsecs away, or this example of an ultraluminous infrared galaxy, you see that this peak of emission in the far infrared rises up very strongly, to the point where if you're looking at an ultraluminous infrared galaxy, more than 90% of the energy can be coming out in this far infrared peak. So for those types of galaxies, if you're studying them in the optical, you're just scratching the surface of optical depth of a few, or maybe probing along a few clear sight lines. You're not, in general, seeing the entire structure of the galaxy. And again, for reference, this is the wavelength and frequency range where ALMA observes in galaxies. So I am interested in studying the gas that is going to form stars in galaxies, and that gas is predominantly in the form of molecular hydrogen. Now, the gas that's going to form stars is typically quite cold, 10 to 50 degrees Kelvin, and relatively dense, about 10 to the 4 molecules per centimeter cubed. Now, molecular hydrogen is a very unfortunate molecule in a lot of ways, because under the conditions, physical conditions in the universe where it is predominantly found, it is completely invisible, because the first emission line it can produce is from the J equals 2 to J equals 0 level, and you need temperatures of about 200 Kelvin in order for collisions to populate that J equals 2 level. So most of the universe where molecular hydrogen is found, we can't see the hydrogen directly. So we use other molecules as tracers of the molecular hydrogen to understand where it is, how much it is, and probe its physical and dynamical properties. And for this, a lot of times we use carbon monoxide, which is the second most abundant molecule in the universe, at least in the local universe, which is easy to excite because its lowest rotational transition is just 5 Kelvin above ground. So even this very cold gas can easily excite CO. We use other specific molecules to probe different aspects of the gas. Hydrogen cyanide is one that we use to probe the much denser gas associated with star formation, and I'll be showing you some results for that today. Now, there is a second way that we can trace the amount of molecular hydrogen gas in galaxies, and that's by studying the emission from dust grains, assuming a gas-to-dust ratio, and using that to infer the amount of molecular gas. That's a very important and interesting approach, and helps us to get around and to validate some of our assumptions in taking CO emission and going to H2, but I'm not going to talk about that today in my talk. So just as an example for why we would care about studying gas in galaxies, it's been known for some time that star formation in galaxies follows a law which has come to be called the Kennicutt-Schmidt law, or the Kennicutt-Schmidt relation, where the amount of star formation scales with the amount of gas. So this image is from a paper in 2007 by Rob Kennicutt. It's the spiral galaxy M51. And in each of these little apertures, which are about 500 parsecs across, they have measures of the star formation rate and the gas surface density, both the atomic gas and the molecular gas. Now, the atomic points are the points in blue, and there's almost no correlation of the star formation rate per unit area with the gas surface density for H1. But the black and the green points are where we're looking at star formation rate versus the molecular hydrogen, and we can see a fairly tight correlation. And for this particular data set, the slope of that relation is a power law with a slope of about 1.4. So essentially, the gas that is the fuel for star formation and the star formation rate itself are very strongly correlated in normal spiral galaxies. So if we want to understand how the galaxy is going to evolve in the future, we need to know about the molecular gas component. And typically when people look at large samples of galaxies, they may have excellent optical data, they may have excellent mid-infrared data. More and more they're starting to have global atomic hydrogen data, but data on the molecular gas is often missing. And so that's part of the challenge. So if we look at a different molecule, HCN, this is a molecule that when we look at molecular clouds in the Milky Way, like Orion, we see that the regions that produce HCN emission correlate very tightly with the regions where we actually can see young star clusters in the infrared. When we look at the surface density of star formation as a function of the surface density of the dense gas traced by HCN, we see correlations that are actually much closer to linear relations. This is some work by Uzero et al., Antonio Uzero, using the IRAM 30-meter telescope, single-dish telescope. If we look on higher resolution scales, this is work by Molly Gallagher, where this is a mixture of single dish and interferometric data, we see still quite a strong, fairly linear correlation. Here, the difference between these two plots, still star formation rate and dense gas, but each of them has been normalized by the total amount of molecular gas as traced by CO. And that takes away a little bit of the concern that a region in a galaxy that has more gas has more stars. The kind of bigger things have more of everything correlation that we worry about with global measurements of galaxies. So these two studies have been really pushing the envelope of trying to get observations of dense gas in galaxies using here the tracer HCN. So with that as an introduction, I want to talk a little bit about ALMA as a facility, because ALMA is really the facility that is letting us do much larger studies of the molecular gas in galaxies, both nearby universe that I study and also at higher redshift. And look at not just the CO emission, but also these fainter dense gas tracers like HCN. So ALMA is I like to call it the first world telescope. It's got 3 major partners: North America, Europe, and East Asia. And of course, it's built in Chile, so that we have our Chilean partners are involved as well. It is located at a site of 5,000 meters elevation in the Chilean Atacama Desert. The thing that makes it hard to observe these wavelengths from the ground is water vapor, so we go to dry sites and we go to high sites so that we can get above a lot of the atmosphere. ALMA is composed of a total of 66 telescopes. There are 50 telescopes that are each 12 meters in diameter in what we tend to refer to as the main array or the 12-meter array. This is the real powerful heart of ALMA, the really big telescopes that are used interferometrically to produce the high-resolution observations you see. There's a small array of 4 12-meter telescopes that are used as single dishes, and these fill in the missing short spacing data in the interferometer. And then there is the Atacama Compact Array, which is a smaller array of 7-meter antennas that also helps to fill in the missing spacings in the interferometer. So some of you probably know how an interferometer works or knew at one point and may know it very well at the moment, but it's worth, I think, reviewing a little bit how an interferometer works and why we want to build one. So in this thought experiment, these are slides that I got from Alison Peck. We're considering that we have 2 sources on the sky that are fairly close together. They could be a pair of stars, they could be a pair of quasars, a pair of galaxies. And we want to make a sharp image to localize the 2 of them and measure their flux. So looking at a very toy element interferometer with 3 telescopes here, if we look at one of these stars, we see that the path the radiation has to travel to each telescope is slightly different. And so that means that the signal from the star will arrive at the different telescopes at different times. That's actually not a very interesting fact. It's simply to do with geometry. We can know exactly what the delay is between the signals at the 3 telescopes, and so we compensate for that delay in the software, so that from one of these sources, all the wave, you can think of the wavefront from the source arriving at each telescope at the same time. But if we have set the delays so that the signal from this telescope arrives, the same wavefront arrives at each telescope at the same time, we cannot make the same thing true for its neighboring star. And so the signal from a different point in the sky arrives at slightly different times at each antenna. That's the phase of the interferometry signal. And it's that different arrival time, that difference in phase, is the signal that lets us figure out where this object is in the sky, and the combination of the phase and the strength tells us the strength of the source. So what we are actually doing, if you look at a little bit mathematically, here is a thought experiment of a source on the sky. So this is towards the North Pole, and this is our east-west baseline. What we measure when you take data with an interferometer like ALMA is samples of the Fourier transform of the sky. So instead of being declination and right ascension, we now have coordinates u and v, and it's a Fourier transform. So the brightness on the sky, T, is related to the visibility distribution by a Fourier transform. And so if we've measured a bunch of these visibility functions, we can then transform it back and recover the image on the sky. And that's essentially, in a nutshell, how interferometry works. So as a visual example, what would happen if you had a pair of antennas, just two, and you observed very briefly a source on the sky? You would not be able to say where the source is. The response of this pair of antennas on the sky is this pattern, which looks a bit, in one direction it's a Young's double slit experiment, and in the other it essentially extends fairly out towards infinity. So we can't really tell much about where the source is. So here are our two antennas on position on the ground, and they give us 2 points in the plane, UV plane, that is our visibilities. If we add a third antenna and take a short observation, we're actually starting already just with 3 antennas to start to be able to localize the source. I did my PhD thesis at Caltech with an array with 3 antennas. It wasn't this bad, but what we did was we would observe the source for many hours, and so you get these little rotating tracks, which you'll see in one of my next slides. If you have 8 antennas, you actually start to be able to say where the source is, and if there was another source over here, you would be able to see that source as well. When you have 16 antennas, this is what ALMA had on day 0 when it started observing. This is what your snapshot observation would look like. Not a bad response function to the sky. With 32 antennas and integrating for 8 hours, each pair of baselines probes a track in the UV plane. You can sample the UV plane very well and get essentially a point spread function or your synthesized beam that looks very, very clean. So this is why interferometers want to have many antennas, because it helps you to probe the Fourier transform of your image plane. Now, ALMA is actually a spectroscopic machine, and for those of you who've worked with radio data or who've worked with IFU data like from MUSE, you'll be familiar with this concept. So our data from ALMA is always a spectral cube. We have position on the sky, right ascension and declination, and then for each point in the image we have a spectrum. And so we can extract a slice in the plane, we can extract a spectrum at a point, all kinds of interesting things we can do. So that third dimension is frequency, and for nearby galaxies we convert that into Doppler shift for velocity. Okay, so with that introduction to ALMA, I want to go on now and talk about some of the scientific work that my group and I have been doing looking at extreme galaxy systems. So just to give you a little bit of context, ultraluminous infrared galaxies were discovered with the IRAS satellite in about 1983 or 1984, so before I began my PhD thesis at Caltech. They were unusual objects. People didn't know what they were. The nearest one was known to be a galaxy. It was ARP 220, which you'll see later in this talk. So people went and looked at these infrared galaxies with CCD cameras, and these are contour plots of optical images showing the disturbed morphology, double nuclei, tidal tails. This is a nice image from about almost 20 years ago now with, in the near infrared from HST, of a handful of these galaxies. This is ARP 220, showing again the disturbed morphology. So what was discovered quite quickly was that all the galaxies with infrared luminosities above 5 × 10⁻¹1 solar luminosities were interacting galaxies or close galaxy pairs. So something about the galaxy interaction or the galaxy merger is bumping up the infrared luminosity. And the underlying physical source of that increased infrared luminosity is mostly formation of new stars. On average, there's a bit of contribution from an AGN, maybe 30% on average, but for most galaxies, it's tracing recent massive star formation. So we can look at these luminous and ultraluminous infrared galaxies and look at the star formation law. And this is a paper that I published earlier this year with Bruce Elmgreen and my students, Ashley Bemis and Nathan Brunetti. And so we're plotting here using CO to trace the molecular gas mass, the star formation rate as a function of the gas surface density. And we are using 5 luminous, ultraluminous infrared galaxies. What's unusual about this paper is that we have resolved the emission in these galaxies, and this is entirely due to ALMA. The resolution of these data is between 150 and 190 parsecs in galaxies where the distances range from about 40 to about 200 megaparsecs. So you could not do this without ALMA. We're using radio continuum as our star formation rate tracer because the high gas surface densities correspond to hundreds or thousands of magnitudes of optical extinction, and so you cannot get a good measure of the star formation rate using traditional optical tracers. So in our Kennicutt-Schmidt law, we find a power law relation with a slope of about 1.7, plus or minus 0.1-ish, and that's quite close to the slope that's predicted from some theoretical work by Bruce Elmgreen over the last 5 years, what you would expect for a galaxy where the interstellar medium was dominated by molecular gas and you were effectively in a pressure-driven equilibrium. One of the other things we realized we could do with the data set was to make an estimate of the vertical scale height of the gas, assuming the gas is organized in a disk. And the scale height is proportional to the velocity dispersion of the gas. It's basically a gravitational balance. The velocity dispersion is telling you how much the gas can move up and down, and the gas surface density is telling you what's the gravity that's trying to hold it down. And the balance between those two gives you the vertical scale height. So when we looked at the vertical scale height in these systems, that plot is shown here. This is a log scale. But on average, the scale height is between 150 and 190 parsecs, and doesn't vary very much over a factor of about 30 in gas surface density. Now, with that scale height, we can infer a mean density for the gas, and that lets us calculate the freefall time, which is shown here. And for the freefall time, the scale down here for reference, this is 1 million years, and this is 20 million years. So the freefall time of the gas on a several hundred parsec scale is a few to the few tens of mega years. It's incredibly rapid. These galaxies, and this is probably part of the reason why these galaxies are forming stars so rapidly. And the final quantity that we calculated, which is of interest to simulators, is the efficiency per freefall time, the star formation efficiency per freefall time. And again here, we're seeing something that doesn't vary very much with gas surface density and is 5 to 7%. This also is relatively high compared to what people think is going on in galaxies like our Milky Way. People typically think this efficiency per freefall time is about 1% in normal spiral galaxies. So probably two things, the high efficiency per freefall time and the short freefall time, are important factors in understanding why these galaxies form stars at such an incredibly fast rate. I just want to highlight, before moving on, a couple of works from a couple of my students. So Nathan Brunetti is working on an extremely high resolution data set for the luminous infrared galaxy NGC 3256. We have 40 parsec resolution data in this galaxy at 44 megaparsecs, so that's about 1/10 of an arcsecond resolution CO data. And he's going to be able to compare the cloud properties with the FANGS sample. This is data from a paper by Jai Sun I'm sorry, I should have put the reference on here, for the first 15 galaxies from the FANG sample. So that's Sun, Leroy et al. 2018. So one of the things that's interesting, this is plotting the distribution of the peak brightness temperature of the gas. So here's 3256. In the center, the peak brightness temperature is about 10 Kelvin, and that's quite a bit high, and the mean for the whole galaxy is maybe about 5 Kelvin. Quite a bit higher than what's seen in normal spirals. And a higher brightness temperature is actually something that some of the theoretical models have predicted in trying to understand the interstellar medium and how the CO emission is produced in galaxy mergers, work by people like Dashiki Narayanan. Another of my PhD students who's co-supervised with Dr. Laura Parker at McMaster has been working on the Kennicutt-Schmidt type relation, but using the edge sample of spiral galaxies. And one of the things he's been testing is, does the global Kennicutt-Schmidt relation, which is the blue points, and a resolved Kennicutt-Schmidt relation agree? And he is generally finding that they agree pretty well, which is perhaps not unexpected, but is one of those good to confirm facts. So another topic related to Euler's that I want to talk about a little bit is CO isotopic ratios. So mostly when people observe carbon monoxide, they're looking at the most common isotopic form of it, which is 12 carbon, 16 oxygen. But there are isotopes, so you can look at 13C16O or 12C18O. In our own Milky Way, 13CO is about 10 times fainter than 12CO, and C18O is about 5 times fainter still. So that's a normal pattern for a spiral galaxy. Work by my former student Kaz Sliwa, published a couple of years ago, showed, though, that in one of these ultraluminous infrared galaxies, the C18O is very strong and, in fact, is brighter than 13CO in many regions of the galaxy. And that's really surprising. People know about the 13CO and C18O being weak, but seeing C18O brighter than 13CO was unexpected. Now, for his PhD thesis, Kaz had been studying a number of these merging galaxies and had been able to model to determine the actual abundance ratio of 12CO relative to 13CO, and found a high abundance ratio in these galaxies. In our own Milky Way, that abundance ratio is about 50, but in these starbursting and merging galaxies, it seems to be more like 100 to 200. So this actually had been, the abundance ratio wasn't known, but the line ratios, being unusual, were already known more than 25 years ago. And a paper by Casoli et al. Talked about how could you get a very low 13CO abundance relative to 12CO, and came up with two explanations that seemed to be viable. One is that the merger was causing gas in the outskirts that was not yet enriched too much to flow into the center, and that would give you a low 13CO abundance relative to 12CO. And the second is that if you had a very young starburst, the massive stars in that starburst could pump a lot of 12 carbon, so produce 12CO, back into the ISM more quickly than you would get the 13CO, which comes from intermediate mass stars. There's another alternative that wasn't considered in Casoli et al., which is if you have a top-heavy initial mass function in a starburst, you can get an interstellar medium that's enriched in 12CO and also relatively enriched in C18O, because both 12 carbon and 18 oxygen come from massive stars. So what we concluded in the 2017 paper was that we needed either a top-heavy initial mass function or an extremely young starburst to explain the ratios that were seen in this galaxy. So my postdoc, Toby Brown, used data from the ALMA archive to look at 3 additional galaxies, and then also to look at the same one from the Sliwa et al. Paper again. And these figures are showing you C18O and 13CO for each galaxy, and they're on the same brightness scale. So here in ARP 220, C18O is brighter than 13CO. Here, brighter, here, this one's brighter, here, brighter. So we're seeing this pattern of enhanced C18O so far in all of these galaxies that we've looked at. And there's other work by Romano et al. And Zhang et al. In nearby galaxies and galaxies at high redshift. The more galaxies we see with this unusual abundance ratio, the harder it is to believe that they're all due to an extremely young starburst. It's not out of the question, but it becomes harder the more examples we have. The other wild card, of course, is always that maybe we don't understand astrochemistry as well as we think we do, especially on a few hundred parsec scales. And so that's something actually to keep in mind as we go forward. But at the moment, the evidence is pointing for a top-heavy initial mass function. Okay, the second piece of my science results I wanted to talk about was studying dense gas. And specifically looking at the antennae galaxy merger. So this is a beautiful optical picture of the antennae published by Whitmore et al. And I think this was in 1999. And you can see the nucleus of one of the galaxies is here, the other nucleus is here, and contours of HCN are overlaid on that plot. It's a little hard to see those contours, so what we have over here is a color plot where we're looking at the ratio of HCN relative to CO. Red values are higher ratios, blue values are lower ratios. And what we found, my former student Max Scherm in a paper in 2016, is a relatively high ratio of HCN to CO in the nuclei of the two galaxies compared to this region, which is generally called the overlap region, which is where a lot of the star formation is happening. So one possibility is that this high dense gas fraction could be due to high pressure in the centers of the galaxies due to the fact that the gas is living inside the stellar bulge. So my student Ashley Bemis worked on this data some more and brought into the analysis far infrared data from Herschel to measure the star formation rate. And so this is showing you a schematic of the antennae where the contours are the 70 micron emission, tracing the star formation rate. And these colored apertures are showing you the different regions where she was measuring the infrared luminosity and the HCN luminosity. And so here we have a version of the Kennicutt-Schmidt star formation relation with the infrared luminosity versus the dense gas. And again, we see quite a nice linear correlation. But the thing that's interesting is the two nuclei, even though they have a lot of HCN emission, so you would think they have a lot of dense gas, lie towards the lower boundary of the relation between infrared luminosity and dense gas. So it looks like you have a lot of dense gas in the nuclei, but something is preventing that gas from forming stars as efficiently as you otherwise would expect. I'm going to come back to that a little bit at the end of my talk. So about 5 years ago, 6 years ago, I started thinking about another molecule, which is CN. And CN is a dense gas tracer. You can produce CN from HCN by interaction with photons or X-rays. It also can be produced in reactions with ionized carbon and neutral carbon. So you expect CN to be a tracer of photon-dominated or X-ray dominated regions. And from looking at models of those regions, you would predict that you would find HCN in the cold UV shielded regions of gas, and you would find CN in the warmer outer regions of gas. So I thought, well, CN was interesting to study because it may trace the dense gas exposed to very recent star formation. But I had a sort of ulterior motive in thinking about CN, and that was this serendipitous fact that with ALMA, you can observe CN every single time you look at CO 1 to 0 in a nearby galaxy. They are only 2 gigahertz apart in frequency, and ALMA's natural setup for observing nearby galaxies has 4 gigahertz. So you put CO in one window, you'd have to try really hard not to get CN in the other window. So I started this project as an archival project, looking at all the data that ALMA had taken in cycle 0. I had data for 17 galaxies, 8 of them with detections, published this in a paper last year. This shows you an example of probably the prettiest galaxy in the sample, again, NGC 3256. We see the northern nucleus has quite a low ratio of CN to CO. No, sorry, CO to CN, and then the southern nucleus has a higher ratio. So variations in this line ratio, typical values of 10 to 20 in CO relative to CN. So with those variations, I realized I should really look at HCN as well, because of the way the chemistry is linked. And so I started a project a couple of years ago where I was going to mine the ALMA archive to try to build up the largest sample of galaxies with CO, CN, and HCN data. And in August 2017, I looked at all the public data on nearby galaxies in the ALMA archive, and I pulled out 12 galaxies for which all 3 of those lines were detected, and they weren't just point sources, they were spatially resolved. Of those 12 galaxies, 3 of them were going to be difficult to work with. One was ARP 220 at super high resolution. One was NGC 253, which is the closest starburst. And another actually was missing the radio continuum data, so we didn't have a star formation tracer. So what I'm going to show you is results for 9 of these 12 galaxies. They are a mixture of Eulergs, starbursts, and spirals, and some of them have Seyfert nuclei, so accreting AGN. And most of the galaxies in this sample have relatively high star formation rates and gas surface densities. So I was lucky enough to have a fellowship, a Killam Research Fellowship in Canada that bought me out of teaching for 2 years. That's how I was able to do this project. I made cubes for these galaxies of these 3 lines and HCO plus and radio continuum with matched beams in each galaxy, and then we bin so that the individual pixels are Nyquist sampled. There are 18 different ALMA projects in this data set. And I realized recently that I should have done more molecules than these, so I may have to go back. This shows you a snapshot view of our sample. So you see the 9 galaxies. The antennae is here because Ashley is using it in her analysis, but I'm not using it in mine because it doesn't have CN data. But these are roughly in order of infrared luminosity up at the top. So this is a Eulerg, this is a Lerg, a Lerg, a Lerg, a merger, a starburst, a spiral with a starburst, a spiral with an AGN, a spiral with a liner nucleus, and I think that one is a starburst and an AGN. So I don't quite know all these galaxies as well as I would like yet. Okay, so just to show you the quality of the data, here is Circe Ennis. This is one of the closest galaxies in our sample. It is a spiral galaxy with an AGN in the center. So this is what the CO map looks like. And for scale, here's 300 parsec resolution. We're going to zoom into the center, which is where the line ratios and radio continuum are detected. And so this is a plot of the HCN to CO ratio. And so you can see that there's a range of about a factor of 3 or 4 in brightness from the center, which happens to be near the AGN, to the outskirts. This is what CN to CO looks like, fairly similar to HCN and CO. And this is what CN over HCN looks like. A very, very flat distribution, maybe a little bit higher in the center, but not a lot of dynamic range in the ratio in this map. And this pattern of very constant CN to HCN ratio is seen across all 9 galaxies in our sample. These are all 9 galaxies. The mean ratio is 0.9 plus or minus 0.1 over a star formation rate surface density of more than 2 orders of magnitude. One caveat, a few of these highest points may have AGN contamination in them. I haven't taken that out yet. But most of these points are star formation. And just to show you it's not everything, so here is Cn over Co as a function of star formation rate. And we see a correlation and some interesting offsets from one galaxy to another. So we've got our star formation rate again from radio continuum. We haven't applied corrections yet for AGN or dust. Now, this was really surprising to me, and the reason it was really surprising to me is when you look at models of photon-dominated regions, like this work from Boger and Sternberg about 15 years ago, they predict that to have Cn in abundance, you need UV or X-rays. And they predict significant variations in the abundance of Cn relative to HCN with UV intensity. So a couple of different models here. The pink is keeping the density constant and varying the UV intensity, and the blue is keeping the ratio of the UV to the density constant. But in comparison, that's what our data look like. Very, very flat over the same type of dynamic range. And so it's a little puzzling, and when I get done with the big grant I am working on until January, I will come back to this and try to figure it out. My suspicion is, one suspicion is, that the models I'm comparing to are too simple. They tend to be slab constant density PDR models, which we've known for years do not reproduce the abundance of atomic carbon well. And since Cn links to atomic carbon, maybe they don't produce Cn well. So it would be very interesting if somebody could run a model of a PDR on a clumpy cloud and include the nitrogen chemistry and see if that gives you a very constant Cn to HCN ratio. But nitrogen chemistry is kind of tricky, I'm told, and so it's not usually included in the first attempts that people do for these astrochemical models. And just to come back to the question of the HCN to CO ratio, Ashley Bemis has been working with this same sample, trying to understand the line ratio of HCN to CO and HCO plus relative to HCN. And she has been doing models where she takes the gas density, assumes a log normal PDF with a power law tail, uses different values for the Mach number, convolves that with the excitation of the molecules, and predicts the line brightness. It's a lot to say, and it's fairly complicated, but it's fairly sensible and physical. And so these curves are some plots for her models where you're varying the Mach number and varying the kinetic temperature, the three different curves, and then the splotch of points is the actual data. So we have a wide range of HCN over CO, wider than we see in the models. Maybe we have pressure variations, maybe there are true abundance variations. And the high ratios of HCN to HCO plus are really difficult to recover if you only vary the density and the temperature. So there may be some real variations in abundance going on these scales as well. So just before I finish, I want to advertise the new large program. My postdoc, Toby Brown, is the PI for this. It was accepted for cycle 7. It is called Vertigo, the Virgo environment traced in CO. We're mapping 51 Virgo galaxies using the compact array on ALMA. And so we'll have half kiloparsec resolution maps at about 5 kilometers per second. Because it's Virgo, there's a huge wealth of multi-wavelength data. Just about every wavelength you could possibly ask for has been done in Virgo except for CO. And so now we're doing CO. And the main two key science goals are to map the structural and kinematic properties of the gas in Virgo to try to understand what effect being in a cluster is having on the gas, and also to measure the star formation rate and molecular gas surface density on subkiloparsec scales, looking at that Kennicutt-Schmidt law, again, in the cluster environment. So, in conclusion, I've shown you little vignettes of some of the work that we've been doing, looking at dense gas and star formation in nearby galaxies. We're seeing a steep Kennicutt-Schmidt relation in ULERGs, an unusual isotopic ratio that may indicate a top-heavy stellar IMF. We see high dense gas fractions combined with a low star formation efficiency, in the galactic nuclei of the antennae. And we're just starting to probe this complicated nitrogen chemistry for the dense gas and coming up with some potential challenges for astrochemical models and just even simple astrochemical thinking to try to understand. So, thank you.
Thank you so much for an amazing talk. The room is open for questions. And while people think about, I always want to ask the first question and somebody puts their hand up. So, there you go.
Thank you. For a while I was asking myself what you mean by star formation rate, but then you said it. It's derived from the radio continuum intensity. So my question, what is the connection between the radio continuum and the star formation rate? What's the idea behind that?
Right, so it's a very good question. The radio continuum that we're using is actually at 93 gigahertz, and so it is thermal free emission. It's Bremsstrahlung emission, so that it is ionized electrons streaming around in H2 regions produce radio continuum emission. So it's very directly linked to star formation, the same way that, say, H alpha would be. It's the massive stars ionize the gas, and the ionized gas produces H alpha emission, Paschen alpha emission, and radio free. Yeah.
So it's the total amount of H2?
Yes, you're essentially counting it, like many star formation rate indicators, you're counting massive stars by counting the ionized gas they produce. Yep.
Is that on? Yes, now it is. I was wondering how the unusual isotopic abundance ratios indicate a top-heavy IMF. I didn't quite understand that.
Yeah, so that's a good question. So the basic idea is that is where the isotopes come from. So in stellar nucleosynthesis, the 12 carbon and 18 oxygen, and I think also 16 oxygen, are produced in fairly large quantities in the massive stars. But 13 carbon is produced in intermediate mass stars, like few solar masses, as opposed to above 10 solar masses. So if you had a top-heavy IMF, you would have more massive stars, and therefore they would produce more 12 carbon and 18 oxygen. The trick is not to produce the 12 carbon, that's there all the time. It's the relative abundance of 18 oxygen relative to 13 carbon that's strange. One of the early ideas, which was you had gas that was less enriched metallicity-wise flowing in. If you were doing that picture, you'd expect both 13 carbon and 18 oxygen to be low. But the fact, and to be in their sort of normal ratio. But the fact that the 18 oxygen has come up relative to 13 carbon is what points you towards something has got to have gotten the 18 oxygen into the ISM at a faster rate than 13 carbon. And so a top-heavy IMF would do it, an extremely young starburst would do it, because you're just catching it right when all the massive stars have gone boom, but the lower mass stars haven't had time to evolve.
I mean, on the same topic, before we play with the IMF, I mean, we know that 12CO and 13CO react slightly differently to UV radiation because of the isotopic shift and so on. And so if you have a high density environment, a starburst environment, where you have many UV photons and you do have turbulent high density gas, isn't it conceivable, or wouldn't this be Occam's razor to say that this changes the abundance ratios? I mean, for, let's say, standard conditions, we see that already in some selected clouds.
So you're talking, for example, about fractionation?
Yes, chemical fractionation and UV fractionation.
So the thing, and that's actually, that's discussed in the Sliwa paper. I think the thing about chemical fractionation is you would expect it to also affect C18O. So fractionation could drive the 13CO abundance relative to 12CO, but you'd expect a similar driving of C18O, is my understanding. So you have to have something, you picture you're in a 1 to 10 to 50 ratio, you have to drive the 10 down while not driving the 50 further down. And that's the trick, yeah. So we don't think fractionation can do it.
So we kind of looked into this with the 12 and 13 ratio, but we didn't look at the C18
Yeah.
contribution.
Yeah.
So there could be an interesting test.
Yeah, no, it would be interesting to know, yeah.
So I have a question in the meanwhile on the same topic. So the other alternative you mentioned is to have an extremely young starburst.
Yeah.
You're using free continuum. Doesn't that imply that you're looking at a very young stellar population? Because it's coming from the most massive stars.
Well, I mean, I would say a concern that I do have in this sort of this line of logic is because we are looking at extreme systems, they've been starbursting, and so one of the galaxies is actually a post-merger. So that's the fact that we see the weird ratio there is actually suggests it's not a super young starburst. But what if you had a 10% hiccup burst of star formation, and that's what you're seeing? They're all selected because they're infrared luminous. Maybe that makes you select things that are super young. But to first order, the free radiation traces star formation exactly the same way H alpha would. And so, so the same question could be applied to everything else. Yeah, I have to think about that a little bit, but yeah.
I have another question as well, which relates to the plot with the Mach number. So you showed the change of the HCN to CO ratio with Mach number. Yeah. So the Mach number is driven by two things. There's the velocity dispersion and it's the temperature. Mm-hmm. So which one are you actually measuring here?
This is really predominantly the velocity dispersion, because the gas velocity dispersion in these galaxies is high.
Yeah.
It's much higher. I don't have that plot in my slides, but it's in the Wilson, Elma Green, et cetera paper. Mm-hmm. The velocity dispersions in these galaxies are few tens up to pushing 100. Okay. So the temperature is really a very small perturbation on it.
Okay.
Yeah.
That's fair. Okay. Further questions? If not, then before we thank Chris again for an amazing talk, I would like to first discuss the colloquium dinner tonight. So we're going for the colloquium dinner at 6 p.m. to the Dorfschenke. Anybody who's interested in joining, please come down and talk to us so that we can get a head count for the dinner. And then next week we will have the next colloquium, which is strangely formatted. Let's do that again. All right, there we go. We have the next colloquium, which comes from extreme star-forming environments all the way back to the solar system, where Frank Postberg will be talking about the subsurface ocean of Enceladus, not to be confused with Gaia Enceladus for the galactic archaeologists among you. And with that, let's thank Chris again for a wonderful talk.